now we're going to talk about the Heartycross method, which is a way to extrapolate what we just learned about the junction equation and the loop equation for one branch to a whole network. So what we see here is kind of a simplified pipe network that could be the network for a distribution system, for a neighborhood, city block, that kind of thing. And the idea of this setup here is we have flow coming in, so at 2 points on one side, and then we have flow leaving the system. And then, of course, that flow is going to be partitioned among these different pipes that we have in the system itself. And so to evaluate this problem, typically you're going to be given some inflows and some outflows. And what we're going to do is identify the loops. Loops. And we're going to have M loops. And I'll draw those out in a second. And then we're going to identify the junctions. And we're going to have N junctions. So first, let's do the loops. And we're going to just give them a number. So this is going to be loop number 1, loop number 2, loop number 3, and loop number 4. And then we're going to look at these loops and we're going to say, how is flow moving? But I think before we do that, we're going to say how much flow is coming in. So first we'll have 3 CFS coming in here. We're going to have 1 CFS coming in here. We have 0.5 leaving, and then we have 3.5 leaving over here. So these are the boundary conditions that set up our problem. Now that we've identified the flow coming and going, let's think about how is flow routed through this system. And we're just going to guess. And this is kind of an iterative type of problem. So I'm going to do this with you all. And flow's coming in from here. I'm going to say that it goes this way. And then we'll say that flow continues in this direction and makes its way all the way to the outlet. There's 3 coming in here and 3.5 going here. So I'd imagine that flow is going to be moving in this direction to route it through the system. Of course, we're going to have a little bit of flow going in this pipe. And I think because there's more flow coming in from the top than the bottom, there's going to be essentially more pressure to push flow this way. So we'll say flow goes that way, it goes this way, and then we continue as we go. I'll just say flow continues in this direction. And then we'll say that flow is going to go up here. And then we'll kind of think about which way will flow go. I think that we have kind of a net migration of flow from the left to the right. So we'll draw that arrow. And then there's kind of a lot of flow up here. So we'll say some of it goes down here. And we'll say some of it goes this way. Oh, we already assigned that, so we don't need to do it twice. So I'll erase that. And then do we miss something? I think we got to get these 2. So we'll say to balance things out, we're going to have some flow returning down here and going that direction. So this is an initial guess, and we'll learn next time in class that it doesn't matter if you get it right or wrong. You'll have a chance as we go through this iterative process to adjust your initial guess. The next thing we'll do is partition flow, and we'll just assign numbers to the CFS that are flowing in each pipe. And this can be very simple. We'll say 2 goes in this pipe and 1 goes in this pipe. So we have 1 coming down here and 1 coming in. So this has to be 2 CFS. We'll say that 1 goes this way. We have 2 going over here, 1 going this way. So 1 is going up. And then we have half a CFS leaving. Maybe we'll go up the top before we kind of get in the middle here. So, okay, we've got 2 coming across. We've got, we'll say 1 is leaving and 1 is going across. And then now we got to get to the 0.5s. So we'll say 0.5 is going that way and 0.5 is going that way. And then we've got 1 coming down and 1 coming up. So that has to be 2. And then 2 coming across, 0.5 coming down. So this has to be 2.5. just by keeping that math straight. We've got half a CFS leaving, and we've got 1 coming across. So that is 1 plus 2. That gives us 3, and that all checks out. So now we have 3 half and then 3.5 leaving. All right, so our math is pretty good here, and we do need to make sure that these junction equations all hold, at least for the initial guesses. What is coming in has to be equal to what's going out of a particular junction. All right, now we've got M loops, right? So we have 1, 2, 3, 4 loops. So M is equal to 4. And then we have, let's see how many junctions we have. 1, 2, 3, 4, 5, 6, 7, 8, 9 junctions. To 9 junctions. And so essentially for each of these, loops and junctions, we have these multiple unknowns, right? We have all these unknowns of Qs across these different pipes. So we need what ends up being M plus N minus 1 equations to solve for this thing. All right, so let's get into the process of doing the actual Heartycross method. So I'm going to zoom out a little bit. No, maybe not. We'll just work over here. So I'm going to just kind of like talk about this algorithm that we use, and we'll set up the problem. So at each junction, say, for example, of a particular loop, and we'll look at loop 2. So we've got B, C, D, and E. The total inflow must equal the outflow. And so that's going to be our junction equations. And then the loss of head from flow along one of these pathways has to be equal to the loss of head and flow on the other pathway. And so if we're just looking at loop 2, then we can say the loss of head from flow in the, we'll say counterclockwise direction has to equal the head loss in the clockwise direction. So that's how we're going to decompose these loops for our loop equation. By counterclockwise and clockwise flow paths. So our counterclockwise flow path in this case is going to be pipe BE to ED, and then our clockwise is going to be, if we're starting over here at B, it's going to be BC, or sorry, that's clockwise. I'm getting them mixed up. Our counterclockwise is going to be BC to CD. That's an E right there. All right, and so another way to say this is that head loss counterclockwise is equal to head loss clockwise. All right, so now this is the kind of the basic idea. Let's talk about the actual method to do this. And I'll just say Heartycross method. So first we estimate the flows, the magnitude of the flows, and the direction, like we just did in that figure, in each pipe in the network. Such that Q in is equal to Q out at each junction. And that results in n-1 junction equations, right? If we have n junctions, then we have n-1 junction equations. And then we will use our loop equations. Which is that head loss equation on the first loop that we're interested in. And what that gives us then is you're solving for the head loss and counterclockwise. Is that equal to the head loss in clockwise, given your initial guess? For those cues, you set those cues up, you guess that, you use those cues as inputs into these head loss equations. Do they equal each other? They're probably not, because you're just partitioning half of a CFS or a whole CFS. So then what you do is you're able to solve for the error, which gives you a delta Q. And then that delta Q is how much are you off? You said that Q and the counterclockwise is this, and Q and the clockwise is this. You solve for the head loss. You're able to estimate how much you're off by the head loss because they need to equal each other. You end up with this error term, and then you are able to, so this error term, so solve for delta Q such that head loss in the counterclockwise direction is equal to head loss in the clockwise direction. So this delta Q basically fills that gap and solves it so that you end up with, how much are you off so that these work and that these actually play out. And then the next step is to adjust your initial guesses by delta Q, and I'll show you how we do that. But essentially, you add it to one side and you subtract it from the other to iterate or update your Qs in that particular loop, and then you repeat step 2. You see how far you're off again. Hopefully your delta Q goes down. It's not going to be a perfect adjustment, but it's going to get you in the right direction. And then continue for other loops. And so essentially you're going to be updating the flow rates in each loop and kind of moving ahead and honing in on the flow rate that actually solves this loop equation so that those both sides are equal. And then you're going to repeat this process or repeat iterations until delta Q goes to 0 or some kind of small value that you set, like, say 0.001 or something like that. So you can set this error term. We're going to say our error in terms of head loss is going to be low enough such that our delta Q gets to some small value, and then we go. All right, so I'm going to give you the actual equations and kind of the equation for delta Q, and then we will actually put this together and solve it together in class next week. All right, so let's start with the loop equation. Actually, what we're going to be doing here is solving for that delta Q. So we kind of already know what the loop equation is. We'll give the Darcy-Weisbach equation as F L over D, V squared over 2G, which is equal to, if we kind of break the Q out of there, we say F L over D 1 over 2GA squared. We can treat these as our constants, although we know that F is not a constant and we're not going to do iterations within iterations, right? We're already iterating to find what the flow distribution is. We're not going to iterate on F, but we do have software that does that for us. And then we'll bring out Q squared over here. And then we'll define this term K as equal to all these constant values. And more appropriately, we can say K is equal to, in terms of diameter, because that's usually what we're given. So we'll say length over D to the 5th, pi squared. We got an 8 in there, and then we've got a G. So those, we'll treat all these as constants. So now this gives us a form of the head loss equation as K Q squared. So that's pretty simple. And if we were to set this up in a spreadsheet, we can just plug in all the lengths and all the diameters, and then solve for F, assuming fully turbulent conditions, to get this, calculate this K value for each particular pipe. All right, now we're going to define our loop, and we're going to say the sum of our head losses in the clockwise direction is going to be equal to the sum of our K's in the clockwise direction and times QC squared. And so you could imagine this is going to be for each pipe, right? So each pipe is going to have a flow. Maybe there's 2 pipes, right? So pipe BC and CD or whatever that is, so that you'd sum up the KQ squared for each of those pipes in that flow direction. So I'll zoom back over to this. So we would have a K for pipe BC times QBC squared, and then we would have K for CD times QCD squared, and that would give us our sum of KQ in this case, that would be the counterclockwise direction. So that's what that looks like. I'll zoom back over. And then we'll do the same thing for our counterclockwise. Okay, so we're marching along here. We've kind of set up the head losses in a more simplified way in the clockwise and counterclockwise direction for our pipes. And as part of that algorithm for the Heartycross, we're going to assume initial Q's, and we're going to plug those in to these values to calculate those head losses. And then we're going to say that so these two should equal each other, right? So initially it's the sum of KC QC squared should equal sum of KCC QCC squared, but they're not going to, because we're just making guesses. And so what you end up with is some sort of error. We're going to bring both terms on the same side. And this is going to equal some closure error. We weren't able to close that, so we get some sort of error, right? So what we need then is that delta Q, which is our we'll call it that flow correction factor. And we're going to use this to subtract this error, right? Which is delta Q. We're going to subtract it from the clockwise direction, and this is just a rule that will get us to actually closing that equation. So we'll subtract it from the clockwise Q's, and then we'll add it to the counterclockwise Q's. And ultimately, we're going to keep doing that and iterating it so that we get the head loss in the clockwise is equal to the head loss in the counterclockwise. So let's figure out what that delta Q actually is and how we can calculate it. And then, so the idea is we'll go back to that initial loop equation where we have the sum of our KCs. And in this case, we're going to say we have some actual value, QC, the Q in that clockwise direction. We don't know what that is, and we're trying to calculate that. But we're going to end up with some error term because our initial guess is off. And so we're introducing that error term in there. And we're going to square that, and then we're going to say that's equal to the KCC times QCC plus delta Q squared. So we didn't really change anything other than adding it on one side and subtracting it from the other side. We can bring everything over and, we can kind of factor this out. And so we get sum of KC is equal to, so we'll actually carry out this squaring of these two terms, and we get QC squared minus 2 QC delta Q plus delta Q squared. So we're just carrying out that squaring of those terms, and then we're going to make an assumption here. So we're going to say delta Q is assumed to be relatively small, not small enough to neglect it, but relatively small, such that delta Q squared is approximately 0. So it's not infinitesimal, but if we square it, it's going to be pretty tiny, and we're then going to neglect it. And so that's going to simplify our equation. So if we do that on both sides, and we factor this out over here, we say KCC is equal to QCC squared minus 2 QCC delta Q plus delta Q squared. Then we get to cross those delta Q's out, those delta Q squareds out, because we're saying those are tiny. And then we can solve for delta Q. So delta Q is finally equal to, and this is definitely a mouthful, sum of KC QC squared. So we're now multiplying the KC's into those parentheses, minus sum of KCC QCC squared divided by 2 sum of KC QC plus sum of KCC QCC. All right. This is now our definition of delta Q. It only accounts for friction losses or major losses. I think we would all have brain bleeds if we tried to put in the minor losses there, but again, that's why we have software. And then we'll remember that K is equal to 8FL over pi squared G D to the 5th. And so we can calculate that out in a spreadsheet for each particular pipe that we're interested in. All right, so now we've got our delta Q equation, and that's very fun to type into Excel, I can tell you. But I give you a spreadsheet that kind of gets you set up to do that. And then what you end up doing with this is we make our initial guesses, we calculate delta Q, and then we update the Q's, and we'll say the first loop, so loop 1 that we do it with, using the delta Q equation. And by doing this, we're subtracting from each QC. So they're in this case, if it's a square loop, then there's going to be 2 pipes or 2 QCs. And then we add delta Q to each QCC. This is arbitrary, which you're adding or subtracting is, but you have to pick a rule and stick with it. Otherwise, you're never going to converge on a solution. So this is the Heartycross method, just says do it this way. And then you move on to the next loop. In this case, loop 2, and then you calculate delta Q. You subtract from QCs, and then you add it to QCCs, and then you move on to all the other loops. You do all the loops in one iteration, and then you move on and do the kind of bigger iteration. So there's kind of like, you calculate delta Q for each loop and move on downstream, and then you go back and do it again until we get a tiny enough delta Q. And that's just some threshold that we can define. You know, is it 0.0001 or point whatever? You know, it's going to be dependent on the your tolerance for uncertainty in your design. So we will do an actual example together next time in Excel. So hopefully you can wait for that and not be too anxious about it over the weekend. But thanks for your attention, and look forward to doing that next time on Tuesday.